Hello everyone, today we'll talk about the solution to the problem first completely painted row or column. When we are solving this problem, it might be our first idea to try to simulate this process, and over the course of optimizing this simulation to actually be quite performant, we'll reach a solution. Either an optimized simulation or some other solution, because finally in the solution that I'm going to show you there will be no simulation actually. But let's start from the beginning. If we just simulate this painting and after every step we check if the row or column is painted, then this is one brute solution. Of course, we only have to check for the row or column which we have just painted the cell in. So we paint a cell on some row, some column, only those have to be checked. Okay, that's great. First of all, how do we determine what the row and column is? Because we know what the sequence of values is going to be, but we don't know what the row or column for a given value is. We'll probably have to create an auxiliary data structure to hold it. Just for every value, which row or column is that value on, or in general, maybe just for time points, instead of which value we are painting, we can instead write which row or column we are painting. So that's fine, we can now iterate over steps in our time. And to determine if the row or column is painted, we can either actually paint them and check them, but this is suboptimal because this is linear for every step. Instead, we can do it in constant time by, for instance, remembering how many cells are painted in every row or column, or how many cells need to be painted, which is just the inverse of it. We either start with all the cells or with 0 cells. And that means that we can simulate it using an auxiliary data structure, just iterating over all the steps. We look at the row or column, we mark that there is one more cell painted in the row, in the column, and maybe one of those is now completely painted, we return the answer. But we don't actually have to do it. We don't actually have to simulate it. We don't actually have to do this mapping with an auxiliary data structure. Instead, we can also approach it from a different perspective. That's because for every row and column, we have some values in that row and column, and really the point that interests us when the first time appears where a row or column is painted. It's some cell gets painted in that row or column, and it's the last cell to be painted. Which means that if we know for every row and for every column at which times every value within that row or column will be painted, which is again accomplished using an auxiliary data structure. So we have those values that we'll be painting. So we can enumerate them. So the first index is the time point, the second is the value. So we enumerate all the steps in which we'll be painting our values, and for every value we remember the step at which it's going to be painted. So this is the dictionary called when. And now we can take our matrix, we can go through all the rows and all the values in every row and replace them with the time that this value is going to be painted. So instead of holding the values, we'll be holding the time point at which the value is to be painted. And now the only thing that we need to tell, if we want to say when a given row or column is going to be painted, we can just look at the maximum value in that row or column. So after this mapping, we can simply map the maximum over all the rows and columns of the values that are there. So for every row or column, we'll know exactly the time when that row or column is going to be painted, and the minimum of these is going to be our answer. And the final detail is that we have to iterate over all the rows. That's easy, that's just mapped. And also over all the columns. And to iterate over all the columns, we can transpose the matrix. So we have a list of lists, and every list is a row, and now we want a list of lists where every list is a column. And one way of doing that is to take our matrix and unpack it using this asterisk operator and zip it back together. So essentially zip takes however many arguments we give it, and it'll be creating tuples of the first element from the first argument, second argument, and so on. So here mapped is a list of rows. We unpack it so now every row is separate, and zip will take the first value from every row and package it together. Then the second value from every row, package it together. So this is exactly just the columns that we want. So by zipping the unpacked list of rows, we get this generator will give us columns. We convert it into a list to add it to the original list of rows. So this whole expression is list of rows plus list of columns. Those columns will be tuples, not lists, but we don't care about that. We just have to map the max function over them and take the minimum. This is a pretty short implementation of it, and really the only tricky part is this way of writing a transposition. If you prefer to write a transposition more in a more straightforward and understandable fashion, for instance like a list comprehension similar to this, feel free to do so, and then of course the code will be a bit longer, but it'll also be more understandable.